Look up at the night sky, but know that almost everything out there is invisible. The substance that holds galaxies together, the true cosmic architect, is a ghost we call dark matter. Its identity is one of the greatest scientific mysteries of all time, and the solution might be more incredible than we ever dreamed. We will explore a mind-bending theory that suggests dark matter is not a sea of unknown particles, but a vast population of ancient black holes forged in the first chaotic second of the universe. By the end, you will understand how these primordial black holes could solve multiple cosmic puzzles at once. We will uncover how they might form, why they have escaped detection for so long, and if they could be lurking in our own solar system right now. What does it feel like to live in a universe where most of the mass is made of invisible, timeless fossils? We feel the presence of this cosmic ghost through its immense gravitational pull. Picture a giant, invisible hand gripping a spinning galaxy. The stars on the outer edges should be flung away by their own speed, just as you would be thrown from a fast-spinning merry-go-round. But they are not. Something we cannot see, a tremendous amount of hidden mass, holds everything together with its gravity. This is the primary evidence for dark matter. It does not interact with light in any way. It is not a cloud of black dust or a swarm of planets. It is fundamentally transparent, a shadow that only reveals itself by bending the fabric of space around it. Think of it as an invisible wind. You cannot see the wind itself, but you can watch it push against tree branches and see the leaves dance. Dark matter is that cosmic wind, and entire galaxies are the trees bending under its influence. The scale of this mystery is almost incomprehensible. All the stars, planets, and glowing gas clouds we can observe, everything made from the atoms we understand, accounts for less than 5% of the universe. Dark matter makes up about 27%. That means over 5 times more of the cosmos is made of this invisible substance than of all the visible matter combined. For decades, the leading theory has been that dark matter is a sea of exotic, undiscovered particles. But what if the answer is not a swarm of tiny unknowns, but a universe filled with ancient, invisible holes? For decades, scientists have pursued 2 main suspects in the hunt for dark matter. The first is a class of particles known as weakly interacting massive particles, or WIMP. Imagine a particle that is heavy, perhaps dozens or even hundreds of times heavier than a proton, yet it is utterly aloof. It ignores light and the strong nuclear force that binds atoms. Its only interactions are through gravity and the weak nuclear force, the same force responsible for radioactive decay. This makes it a perfect candidate for the cosmic ghost. It would have the heft to sculpt galaxies with its gravity, while its shy nature would explain why it has remained completely invisible to us. Enormous, sensitive experiments were built to catch one. Detectors were placed deep underground, shielded from cosmic rays by thousands of feet of rock, waiting for the once-in-a-lifetime tremor that would signal a WIMP gentle, weak force nudge. Yet after years of searching, the detectors have remained silent. The predicted sea of WIMP has simply not appeared. The other leading candidate is the axion. This particle emerged from a solution to a different, deeply fundamental puzzle in physics concerning the symmetry of forces. Unlike the heavy WIMP, the axion is theorized to be incredibly light, trillions of times lighter than an electron. But what it lacks in mass, it could make up for in sheer numbers, forming a cold, wave-like mist permeating all of space. Sophisticated experiments using powerful magnetic fields are trying to convert these ghostly axions into detectable photons. The hunt is brilliant and persistent, spanning decades, but like the search for WIMP, it has yet to yield a confirmed discovery. The ongoing silence from these monumental efforts is itself a profound result. It tells us that the universe may not be so simple. The answer might not lie in a sea of tiny particles, but in objects born from the universe's most violent and creative moments. This very absence forces us to look toward more exotic and perhaps more dramatic possibilities. This dead end in the particle hunt forces us to rewind the cosmic clock all the way back to the very beginning. Forget the violent death of a massive star, the traditional birthplace of a black hole. There is another way, a far more ancient and primordial path. In the first fleeting moments after the Big Bang, the entire universe was an unimaginably dense, hot, and turbulent soup. It was not smooth. Think of a pot of water just as it begins to boil, with tiny bubbles and pockets of intense energy forming and collapsing in a chaotic dance. The infant cosmos was like this, a sea of raw energy with random, microscopic regions that were just slightly denser than their surroundings. In that extreme environment, gravity could have performed a magic trick. A region so dense, even if it was only the size of a marble or a mountain, could have collapsed under its own weight instantly. It would not have needed to be a star. It would have bypassed the entire stellar life cycle and collapsed directly into a black hole. These are the primordial black holes, fossils forged not in stellar furnaces, but in the chaotic birth pangs of spacetime itself. Their potential sizes are as varied as the density fluctuations that created them. Some could have been as small as an atom, yet possessing the mass of a mountain. Others could have been as massive as thousands of suns, all forming in less time than it takes to blink. This is not a slow cosmic process, but a spontaneous creation from the universe's most volatile moment. If this theory is correct, our cosmos is not filled with a fine mist of particles, but is instead home to a vast, invisible population of these ancient relics, each one a silent witness to the first second of everything. The trigger for this spontaneous creation was a cosmic imperfection. In the smooth, rapid expansion of the newborn universe, tiny quantum ripples were stretched to enormous sizes. These minute wrinkles in the fabric of spacetime are known as density fluctuations. Think of a perfectly smooth sheet being shaken. It will develop random bumps and dips. The early universe was like that sheet, and those random bumps were regions of space that were just a little bit denser than the areas around them. For most of these regions, it did not matter. The immense outward pressure from radiation and the explosive force of the universe's expansion smoothed them out, but for the rare, exceptionally dense peaks, gravity could win. If a pocket of space was dense enough, its own gravitational pull could overcome all the outward forces trying to push it apart. It would experience a runaway collapse, condensing so much mass into such a small point that a black hole would form in an instant. This is not the slow death of a star, but a sudden, violent pinch in the fabric of reality itself. One leading theory for how these super-dense regions could arise points to cosmic inflation, that period of faster-than-light expansion in the very first fraction of a second. Inflation could have magnified those quantum ripples into the dramatic density contrasts needed for collapse. Another possibility involves cosmic phase transitions. As the hot, young universe cooled, it may have undergone sudden shifts like steam condensing into water. These transitions could have been messy, creating bubbles and defects in spacetime where enormous amounts of energy became concentrated, seeding the birth of a primordial black hole. The very laws of physics suggest that the first moment was chaotic enough to spontaneously forge these dark fossils, leaving behind a hidden population of gravitational ghosts. This incredible birth process means primordial black holes are not all stamped from the same mold. Their potential sizes span an almost unimaginable range. Unlike stellar black holes, which are born from the collapse of massive stars and therefore have a minimum mass several times that of our Sun, these ancient relics have no such constraints. Their mass is a direct imprint of the specific moment they were born in the early cosmic frenzy. A black hole that collapsed when the universe was just a tiny fraction of a second old could be astonishingly small. We are talking about a black hole with the mass of a large asteroid, compressed into a space smaller than a single atom. At the other extreme, a fluctuation that collapsed a mere instant later could have packed the mass of 1,000 suns into a region no larger than our solar system. This is the incredible mass spectrum of primordial black holes. They could be lighter than a feather in cosmic terms or heavier than entire star clusters. The key is timing. The density of the universe was falling rapidly as it expanded. To form a black hole, a region had to be dense enough to overcome the intense radiation pressure. In the very first moments, the universe was so incredibly dense that only a small, mountain-sized region needed to collapse to create a black hole. A split second later, the universe had expanded and thinned out just enough that a much larger volume of space was required to reach the critical density for collapse. This direct link between time and mass is what makes this theory so powerful and versatile. This vast range of possible sizes is the very reason they are such compelling candidates for dark matter. A single type of object born from one mechanism could account for dark matter across all scales. The smallest ones could drift through space like invisible heavyweight dust. The largest ones could be hiding at the hearts of galaxies, mistaken for supermassive black holes born from other means. The cosmos might be filled with a full menagerie of these gravitational ghosts, each a fossil from a different instant of creation. The beauty of this idea lies in its elegant simplicity. A primordial black hole is at its core nothing but pure gravity. It is mass concentrated into a single point. This means that if these ancient objects were scattered throughout a galaxy, their collective gravitational influence would be indistinguishable from that of a hypothetical sea of dark matter particles. They would be the invisible hand gripping the galaxy, holding fast those outer stars without ever emitting a single photon. Their gravity alone would sculpt the cosmos. This solves one of the most stubborn puzzles in astronomy, the rotation curves of galaxies. When we observe a spiral galaxy like our own Milky Way, we expect stars farther from the center to orbit more slowly, just as Pluto moves much more sluggishly around the Sun than Mercury does. But that is not what we see. Stars in the outer reaches whip around at nearly the same speed as those near the core. The only logical explanation is that the galaxy is embedded within a vast, massive halo of something invisible, something whose gravity extends far beyond the visible disk of stars. A population of primordial black holes would create exactly that kind of halo. They would be the unseen anchors, their combined mass providing the extra gravitational glue that keeps the entire structure from flying apart. Their gravitational signature does not end there. According to Einstein's theory of general relativity, massive objects bend the very fabric of space, acting like cosmic lenses that distort the light from objects behind them. We see this effect called gravitational lensing all the time. If a dense cloud of primordial black holes drifted between us and a distant star, its gravity would warp the starlight, causing the star to momentarily brighten in a very specific way. For a time, astronomers actively searched for these telltale flashes, hunting for a class of objects they called MACHO, an acronym for Massive Astrophysical Compact Halo Objects. While those early searches did not find enough MACHO to account for all dark matter, they left the door open for a wider range of masses and distributions of these gravitational ghosts. A primordial black hole does not need to shine, emit, or interact. It only needs to exist, and its gravity does all the talking, bending light and molding the universe on the grandest scales. This makes them a compelling single solution to multiple cosmic problems. The same invisible population that explains why galaxies spin so fast could also be the seeds from which the largest structures in the universe grew. The gravitational wells of these early black holes would have drawn in normal matter, acting as focal points for the formation of the very first stars and galaxies. One type of object born in the first second could be the hidden architect of the cosmos we see today. Yet a critical question remains: if they are everywhere, shaping the universe with their gravity, why have we not stumbled upon one? The story of these gravitational ghosts began not with a discovery, but with a brilliant hunch. In the 1970s, a young physicist named Stephen Hawking, alongside others, turned his mind to the fiery conditions of the Big Bang. He realized the early universe was not just a smooth, expanding fireball. It was a place of such intense chaos that nature could have spontaneously tied space-time into knots, creating black holes from pure density. This was the birth of the primordial black hole hypothesis, a radical idea that emerged from pure theoretical insight. For a time, it captivated cosmologists. It was an elegant, almost beautiful solution. Why invent a new, undetectable particle when the universe's own violent birth could have filled the cosmos with invisible anchors? But then, the idea seemed to hit a wall. Observations began to place tight constraints on their possible numbers. If space were swarming with mountain-sized black holes, for instance, their collective gravity would subtly distort the light from distant quasars in ways astronomers were not seeing. Other searches, like the hunt for the flashes of gravitational lensing, also came up relatively empty. The evidence suggested that primordial black holes could not make up 100% of the dark matter. To many, the case appeared closed. The hypothesis was relegated to a fascinating but fringe idea, a cosmic might have been. Yet science has a way of resurrecting old ghosts. Decades later, the persistent, deafening silence from the underground detectors built to find WIMP forced a dramatic rethink. The leading candidate for dark matter had failed to appear. This absence created a vacuum, and into that vacuum poured renewed interest in the old idea. The resurrection of primordial black holes is a direct result of that failure. It was no longer a question of proving they were the only solution, but of asking if they could be a piece of the puzzle we had prematurely dismissed. New theoretical work gave this revival powerful momentum. The theory of cosmic inflation, which describes the universe's explosive initial growth, provided a robust mechanism for creating the dense peaks needed to form these objects. Furthermore, connections to other puzzles in physics, like the nature of the mysterious dark energy or the search for a unified theory of quantum gravity, opened up new pathways for primordial black holes to form. They were no longer just a curiosity, but a potential bridge between the very large and the very small, a cosmic missing link. The hunt was back on, but this time with a more sophisticated quarry in mind. A brilliant objection arises from the quantum realm itself. If these ancient black holes can be as small as an atom, why does the universe not glow with the light of their explosive deaths? The answer lies in one of Stephen Hawking's most profound discoveries. He realized that a black hole is not entirely black. The violent quantum fluctuations that constantly pop in and out of existence at the very edge of its gravity well, the event horizon, can lead to a slow leak of energy. In a pair of virtual particles, one can fall in while the other escapes, stealing a tiny amount of the black hole's mass. This is Hawking radiation, a faint whisper of heat that causes the black hole to slowly evaporate over astronomical timescales. For a giant stellar black hole, this process is so agonizingly slow it is utterly negligible. But for a small, lightweight primordial black hole, it is a death sentence. The smaller the black hole, the more intense this evaporation becomes. A black hole with the mass of a mountain would have a temperature of billions of degrees, radiating away its substance at a ferocious rate. We can calculate the tipping point. A primordial black hole needs a mass of roughly 1 billion metric tons, about the mass of a large asteroid, to have survived for the entire 13.8 billion year age of the universe. Any smaller than this critical mass, and it would have already evaporated away in a final flash of gamma rays. This sets a powerful lower limit. It tells us that if dark matter is made of primordial black holes, they cannot be lighter than this mountain-sized threshold. The smallest among them must have been hefty enough to withstand the relentless quantum pressure, allowing them to persist as the dark, silent ghosts we are searching for today. This cosmic culling leaves behind a specific population of survivors, each one a heavyweight fossil from the dawn of time. So the question becomes a cosmic census. How many of these ancient black holes can actually be out there without us having already tripped over them? The answer comes from a powerful astronomical technique called microlensing. Think of a primordial black hole as a perfect, invisible lens drifting silently through the void. If it passes directly between our telescopes and a distant background star, its intense gravity will warp the fabric of space around it. This warped space acts like a magnifying glass, bending and focusing the star's light toward us. For a brief period, that faraway star will appear to brighten, then fade, as the black hole moves across our line of sight. The duration of this flash is a direct clue to the mass of the invisible lens. A black hole with the mass of our Sun would cause a brightening that lasts for about a month. One with the mass of Jupiter would create a flash lasting only a couple of days. This is the perfect, unbiased hunt. It does not care if the object emits light, only that it has mass. For years, projects like the Optical Gravitational Lensing Experiment, or OGLE, have meticulously monitored millions of stars in nearby galaxies, watching for these telltale flashes. The Hyper-Subprime CAM survey in Japan has performed similar work on an immense scale. Their collective results have been both definitive and surprising. They have largely ruled out the possibility that primordial black holes within a specific mass range, from about the mass of our Moon up to the mass of Jupiter, can constitute 100% of the dark matter in our galactic halo. The universe is simply not blinking enough. We are not seeing the countless flashes of light we would expect if this particular weight class of black holes were the sole culprit. This does not mean they do not exist. It means they cannot be the entire story. The dark matter halo cannot be packed solid with planet-sized or star-sized gravitational ghosts. The microlensing searches have effectively closed a major window, telling us that if these objects are out there, they must be either much smaller or much, much larger than we once thought. This classic divide in cosmology pits objects against particles. On one side, we have the MACHO, the massive astrophysical compact halo objects. These are exactly what they sound like: hefty, tangible things like ancient black holes, faint stars, or rogue planets that simply do not glow. On the other side, we have the WIMP, the weakly interacting massive particles, an ethereal sea of undiscovered subatomic specks. For a long time, it seemed like a straightforward either-or proposition. The universe was filled with one or the other. The MACHO project, a pioneering search in the 1990s, aimed to settle this by staring at the stars of the Large Magellanic Cloud, a small galaxy orbiting our own. For years, its telescopes watched for the characteristic brightening that would signal an invisible MACHO drifting through the galactic halo and lensing a background star. The results were a landmark moment. They found some flashes, yes, but not nearly enough. The data suggested that MACHO, at least in the mass range of a tenth of our Sun up to a few solar masses, could only account for a small percentage of the dark matter halo, perhaps 20% at most. This was a powerful blow to the idea that all dark matter was made of large, invisible objects. It seemed the case was closed, and the evidence pointed squarely toward the WIMP, the particle solution. The physics community largely pivoted, pouring immense resources into building ever more sensitive detectors deep underground, waiting for a ghostly particle to ring a bell that never sounded. This historical pivot is crucial. It explains why the search for particle dark matter dominated for decades, and why the idea of primordial black holes was pushed to the sidelines. But science, like the universe, is not static. The persistent failure to find WIMP has forced a dramatic re-evaluation of that either-or thinking. We are now entering an era of the mixed dark matter model. The modern revival of primordial black holes does not require them to be the sole hero of the story. Instead, they could be a key component of a cosmic ensemble. Imagine dark matter as a diverse population. Perhaps 10% of it is made of asteroid mass primordial black holes, another 30% is in the form of planet-sized ones, and the remaining 60% is still some form of exotic particle we have yet to discover. This blended model is far more flexible and can neatly sidestep the constraints that doomed the simpler all-or-nothing theories. The MACHO project did not prove primordial black holes do not exist. It proved they are not the only actors on the stage. Our galactic halo could be a much more interesting place than we thought, a shadowy realm populated by both ancient gravitational fossils and a sea of elusive particles, together weaving the invisible fabric of the cosmos. The silence of the particle detectors was broken not by a whisper, but by a shudder in the cosmos itself. In 2015, a new era of astronomy began when the LIGO observatory felt the fabric of space-time ripple. It was the vibration from a pair of black holes over 1 billion light-years away, spiraling into each other in a final, violent dance. This was our first direct detection of gravitational waves, and it opened a window into the dark universe we had never had before. These waves are not light or particles. They are literal vibrations in the geometry of space, generated by the most cataclysmic events imaginable. Every time LIGO and its European counterpart, Virgo, feel another tremor, they are listening to the universe's deepest, most powerful conversations. And in the data from these collisions, a tantalizing clue has emerged. Some of these merging black holes are peculiar. They fall into a mass range that is awkward for traditional astronomy. Standard stellar evolution struggles to explain black holes that are tens of times the mass of our Sun. A star heavy enough to leave such a large corpse would likely blow itself to pieces in a supernova, leaving nothing behind. So where did these hefty objects come from? One compelling answer is that we are witnessing the mergers of primordial black holes. These would not be the remnants of dead stars, but ancient fossils, finding each other in the vast dark of intergalactic space over billions of years. Their unusual masses are not a problem for the primordial theory, they are a prediction. The chaotic early universe could have easily forged black holes of 20, 50, or even 80 solar masses, a perfect match for the strange signals we are now recording. Each tremor from a distant merger could be the echo of a creation event from the first second of time, a ghost from the beginning finally announcing its presence. The echoes of that first cosmic second are still visible today, etched across the entire sky. This is the cosmic microwave background, the faint afterglow of the Big Bang itself. When we map this radiation with incredible precision, we are essentially looking at a baby picture of the universe, frozen in time when it was just 380,000 years old. In this snapshot, we see subtle patterns, a mottled tapestry of slightly warmer and cooler spots. These are the fossilized imprints of sound waves, the echoes of pressure waves that rippled through the hot, dense plasma of the infant cosmos. It is within these ancient ripples that primordial black holes leave a second, more subtle signature, one that can either make or break their case as dark matter. The formation of a black hole is an incredibly violent event, a sudden and immense injection of gravity into the cosmic soup. If vast numbers of primordial black holes had formed all at once, their birth would have been a thunderous roar in the early universe. Each collapse would have sent powerful gravitational shocks through the surrounding plasma. Think of tossing a handful of heavy stones into a still pond. The resulting splash and the ripples that spread out would disrupt the pond's natural, gentle waves. In the same way, the explosive birth of countless black holes would have violently disturbed the universe's natural sound waves, scrambling the delicate pattern we now see in the cosmic microwave background. Satellites like Planck have mapped this pattern with exquisite detail, and the data tells a very clear story. The observed ripples are too smooth, too regular. They do not show the kind of dramatic scarring or excessive clumping that would be expected if a huge population of primordial black holes had formed in a specific, widespread way. This places a powerful and stringent constraint on the theory. It tells us that primordial black holes could not have been so numerous that their collective birth cries overwhelmed the early universe. They cannot be the dominant form of dark matter if they formed in a single dramatic burst that left an obvious mark on the cosmos. This does not mean they do not exist. It simply means they must be more subtle, perhaps forming over a wider range of times or in smaller, more isolated numbers, their individual births lost in the overall cosmic hum. The cosmic microwave background acts as a strict referee, ruling out the most dramatic versions of this ancient story while still allowing for a quieter, more distributed population of these gravitational ghosts to persist in the shadows. But what if the dark matter haunting our galaxy is not a single type of ghost, but a whole spectrum of them? The most elusive could be the planetary mass primordial black holes, objects with the weight of an asteroid or even Mars, compressed into a point smaller than a single atom. These would be the stealthiest of all. They are far too small and light to create the month-long microlensing flashes that surveys like ogle are designed to catch. Their passage would warp starlight for only a few hours or days, a blink too brief for most wide-field telescopes to reliably catch and catalog. This is the perfect hiding place. A vast, dark ocean of these mountain-to-planet-sized fossils could drift through the galactic halo, completely invisible to our primary lensing searches, yet their combined gravity could still account for a substantial fraction of the dark matter we feel. Their subtle influence might be written in the frozen outskirts of our own solar system. Far beyond Pluto, trillions of icy bodies make up the Oort cloud, a vast spherical shell of cometary nuclei. The gravity holding this shell in its delicate balance is a fragile thing. The quiet passage of a planetary mass black hole, even from a distance of 1 trillion miles, would be like a stone thrown into a still pond. Its gravitational tug would send ripples through this cloud, subtly perturbing the orbits of countless comets. Some would be nudged inward, beginning a long fall toward the Sun, while others would be flung out into interstellar space forever. We might one day trace a sudden, unexpected shower of new comets from deep space back to the unseen passage of such a gravitational ghost. The most mind-bending possibility is a direct encounter. What would happen if one of these planet mass black holes passed directly through the Earth? The event would be nothing like a cataclysm from a science fiction film. With a physical size smaller than an atomic nucleus, it would slice through our planet like a bullet through a cloud of smoke. The only damage would be along an impossibly thin microscopic tunnel. A few atoms along its path would be vaporized by the intense tidal forces, but the effect on a planetary scale would be negligible. There would be no earthquake, no explosion. We might not even notice at all, unless we had an exquisitely sensitive network of seismometers listening for the unique, straight-line tremor of such an event. This is the ultimate cosmic phantom, an object with the mass of a world that could pass through our own without leaving a trace, a silent reminder that the darkness between the stars is not empty. This very same mechanism could solve one of the most persistent mysteries at the heart of every galaxy. We now know that supermassive black holes, weighing millions or even billions of suns, lurk in the centers of nearly every large galaxy. The puzzle is not that they exist, but that they existed so early. Astronomers have found fully grown supermassive black holes shining as brilliant quasars when the universe was less than 1 billion years old. This presents a serious timing problem. How could a black hole grow so massive so quickly from a standing start? Even if it feasted on gas at the maximum possible rate, there simply has not been enough time for a small, stellar mass black hole to balloon into such a colossal object. The cosmic clock seems to be broken. The solution might be that these giants did not start small. They were born with a massive head start. A large primordial black hole, forged in the first second with the mass of 1,000 suns, would be the perfect seed. It would not need to grow from nothing. It would already be a deep, pre-existing gravitational well, a ready-made anchor in the chaotic early universe. When the first clouds of gas began to coalesce into galaxies, this heavy seed would be waiting at the center, its immense gravity immediately beginning to pull in vast amounts of matter. This process, called accretion, would be supercharged from day one. Instead of a tiny pebble trying to gather a mountain of sand, you have a boulder gathering smaller rocks. The growth is exponentially faster. A primordial seed bypasses the slow, initial phase of building mass, allowing a supermassive black hole to reach its staggering size within the tight time frame the early universe allows. This elegant idea gives these ancient fossils a starring role in cosmic evolution. They are not just passive dark matter, but the active architects of the most dramatic structures we see. The very black holes that power brilliant quasars and govern the fate of entire galaxies could have their roots in the violent, fleeting moments of creation, a direct link between the very small quantum ripples of the beginning and the very large giants that rule the cosmos today. These primordial black holes do not have to be born from simple, random lumps. Modern cosmology paints a far richer picture of their potential origins, connecting them to the most exotic ideas in theoretical physics. Think of the early universe not as a smooth soup, but as a cosmic workshop where the very laws of physics were still settling into place. In this chaotic environment, defects could have frozen into the fabric of spacetime itself. One such defect is a cosmic string. Imagine an infinitely long, incredibly thin thread of pure energy, thinner than an atom yet so dense that a single inch could weigh more than a mountain range. These theoretical filaments, vibrating and snapping throughout the young cosmos, could have coiled into knots of such immense density that they spontaneously collapsed into black holes. Another possibility involves domain walls, vast two-dimensional sheets of concentrated energy separating regions of space with different fundamental properties. If one of these walls became unstable and crumpled, the resulting concentration of energy could be enough to birth a primordial black hole. These are not random fluctuations, but the structured scars of a universe undergoing a phase transition, like cracks forming in ice as it freezes. The most profound connection may lie with the theory of inflation. While standard inflation produces the gentle ripples we see in the cosmic microwave background, certain specialized models can generate dramatic, sharp peaks in density. In these scenarios, the universe's explosive expansion could have magnified tiny quantum bumps into towering overdensities, perfect for triggering black hole formation on a wide range of scales. This directly links the existence of these dark matter candidates to the specific physics of the universe's very first moment. Perhaps the most mind-expanding idea is that these objects are a signature of a multiverse. In this framework, our universe is one bubble in a vast, frothing cosmic foam. When new bubbles form and collide, the immense energy released at their boundaries could see the creation of primordial black holes. In this view, a black hole drifting through our galaxy might not just be a relic from our beginning, but an artifact from a neighboring reality, a permanent imprint from a long-ago collision with another cosmos. These refined theories show that the hunt for primordial black holes is no longer a fringe pursuit. It is a vibrant, evolving field that touches on quantum gravity, string theory, and the ultimate structure of reality. Finding one would not just identify dark matter, it would provide a direct window into the most extreme physics of the primordial universe and perhaps what lies beyond it. A passing black hole can do more than magnify a star. It can turn the entire universe into a cosmic-scale laboratory, revealing objects far smaller than any telescope could ever see. This brings us to one of the most subtle and brilliant observational tests ever conceived, an experiment that uses the wave nature of light itself. When we think of light, we often picture it as a stream of tiny particles. But light is also a wave, and at the incredibly small scales of gamma rays, this wave-like behavior becomes the dominant feature. The crests and troughs of these high-energy light waves are unimaginably tiny. Now imagine a primordial black hole with the mass of a large asteroid drifting silently through space. Its physical size would be smaller than a single atom. If this minuscule gravitational ghost passes directly in front of a brilliant, distant beacon known as a gamma-ray burst, something extraordinary should happen. The black hole's intense gravity would bend the gamma-ray light, but it would bend the light traveling along one side of it slightly differently than the light traveling along the other side. Think of a rock in a stream splitting the water into two separate streams that flow around it. When those two streams meet again on the other side, their waves interfere with each other. If the crests line up, they create a brighter wave. If a crest meets a trough, they cancel each other out. This is the principle of interference. In the case of our asteroid mass black hole and the gamma-ray burst, the two paths of light would reunite in our telescopes, creating a complex interference pattern etched into the burst spectrum. The energy of the gamma rays would appear to ripple, with some colors being amplified and others suppressed. This effect is called femtolensing, with femto referring to the mind-bogglingly small scale of the lens. It is a perfect direct probe for these specific mountain-sized black holes. Yet, when astronomers meticulously analyze the light from these cosmic explosions, they do not see the telltale interference fringes. The gamma-ray spectra are smooth. This absence of a signal is in fact a powerful discovery. It tells us that space cannot be densely populated with primordial black holes in this particular mass range. If it were, every brilliant gamma-ray burst would be filtered through these tiny lenses, and their light would consistently show this distinctive scrambled signature. The fact that it does not places a severe constraint on the theory. It challenges models where a large fraction, or even all, of the dark matter is made of these asteroid mass fossils. The universe, it seems, has used its most violent explosions to rule out an entire class of hidden objects, forcing the hunt for dark matter to look elsewhere, or to consider a much more diverse and sparse population of these ancient gravitational ghosts. The hunt for these cosmic ghosts is about to enter a new golden age, propelled by a fleet of next-generation observatories with unprecedented vision. Leading the charge is the Nancy Grace Roman Space Telescope, a powerhouse instrument set to monitor hundreds of millions of stars at once. Its wide-field camera will perform a continuous, all-sky microlensing survey of staggering precision. Where previous searches caught a few dozen possible events, Roman is expected to detect thousands. It will be sensitive to flashes caused by objects across a vast range of masses, from something as light as Mars to something heavier than Jupiter. This will allow us to conduct a complete cosmic census for gravitational phantoms in our galactic halo. If a significant population of primordial black holes is drifting through the darkness, Roman will see their shadows flickering across the galaxy, finally quantifying their numbers or ruling them out with definitive statistical certainty. But what about the mergers we cannot see with light? The Laser Interferometer Space Antenna, or LISA, will listen for them. This ambitious mission will consist of 3 spacecraft, flying in a perfect triangular formation millions of miles apart, connected by lasers. It is designed to detect the low-frequency gravitational waves that are completely invisible to ground-based observatories like LIGO. These are the ripples from the slow, stately dance of much smaller black holes. LISA could hear the mergers of primordial black holes with masses ranging from a fraction of our Sun's mass to several thousand times that mass. If the early universe produced a vast population of these objects, their countless mergers would create a persistent, low hum of gravitational waves, a background chorus of whispers from the dawn of time. LISA instruments are so sensitive they could tune into this specific cosmic frequency, providing undeniable evidence that the dark universe is filled with these ancient colliding fossils. The final piece of the puzzle will come from even more detailed maps of the universe's first light. Future experiments aiming to observe the cosmic microwave background will have resolution so sharp they could detect the subtlest of scars. While the overall pattern of the CMB is smooth, the explosive birth of an individual primordial black hole would have left a unique circular signature in the plasma, a faint fingerprint of its sudden gravitational injection. Advanced telescopes, perhaps stationed at the quiet, frigid Lagrange points far beyond the Moon, will scan the microwave sky for these tiny, telltale imprints. Finding them would be like discovering the birth certificates of dark matter itself, pinpointing the exact moments and places where space-time first tied itself into these eternal knots. Together, these observatories represent a coordinated assault on the invisible. They will use gravity itself in the form of bent light, rippled space-time, and primordial sound waves to finally answer the question that has haunted astronomy for decades. Are we living in a universe shaped by the silent, enduring presence of black holes from the very beginning? The James Webb Space Telescope is peeling back time, revealing a universe in its infancy. Its deepest images show us the very first galaxies, glowing from an era just a few 100 million years after the Big Bang, and what we see is deeply puzzling. These ancient galaxies are not the small, chaotic blobs we expected. They are massive, mature, and incredibly structured, filled with more stars than our models can easily explain. It is as if we opened a history book to the first chapter and found a fully formed civilization already thriving. The cosmic clock seems broken. How did these giants assemble so quickly? Something must have given them a colossal head start. The gravitational pull of a hidden population of primordial black holes could be that very catalyst. Think of the early universe as a dark, featureless plane. The first clumps of normal matter, hydrogen and helium gas, were incredibly sparse and slow to coalesce. Gravity from visible matter alone would have taken far too long to pull together such magnificent structures. But now, seed that plane with deep, pre-existing gravitational wells. A population of primordial black holes would act as natural anchors, their intense gravity drawing in the surrounding gas at a dramatically accelerated rate. Each black hole becomes a focal point, a ready-made foundation for a future star cluster or even an entire galactic core. This is not a slow, gentle gathering. It is a rapid, targeted collapse. The presence of these ancient fossils turns a sluggish process into a cosmic sprint. Where gas would have slowly drifted, it now flows swiftly into these invisible traps. Stars ignite sooner, galaxies form faster, and the universe lights up with a brilliance that matches what the James Webb Telescope now observes. This elegant solution explains the impossible maturity of these early galaxies without rewriting the laws of physics. It simply provides the missing architectural framework, a hidden scaffolding of gravity that allowed the cosmos to build itself with breathtaking speed. This direct link to one of the most profound modern puzzles has catapulted primordial black holes from a fringe idea to a central topic in cosmology. They are no longer just candidates for dark matter, but potential architects of the cosmic dawn itself. This elegant compromise resolves the many conflicting clues we have gathered. The universe is not forcing us to choose just one dark matter candidate. Instead, its complex behavior points toward a mixed composition, a cosmic partnership between the ancient and the ethereal. Picture dark matter not as a single monolithic entity, but as a diverse ecosystem of the unseen. Perhaps 10% of the dark matter halo consists of primordial black holes with the mass of a large asteroid. These gravitational fossils drift like invisible boulders through the void. Their collective gravity is significant, but their numbers are sparse enough to avoid creating the constant flickering of starlight that would have been detected by microlensing surveys. They slip through the observational net. The remaining 90% could then be composed of an ultralight particle, such as the axion. This particle would form a smooth, cold quantum mist that fills the spaces between the black holes, its collective gravity providing the dominant, gentle pull that shapes the cosmos on the largest scales. This hybrid model is not a sign of failure, but a testament to the universe's intricate nature. It is a solution of elegant balance. The asteroid mass black holes are too small and fleeting in their lensing effects to be easily seen by current surveys, neatly sidestepping the constraints from projects like OGLE. Simultaneously, the action's ghostly nature means it would not produce the signals expected from heavier particles like WIMP, explaining the decades of silence from deep underground laboratories. This dual approach even provides a compelling answer to the puzzle of the early galaxies. Those primordial black hole seeds, even if they are only a small fraction of the total dark matter, would have provided the crucial gravitational anchors to kickstart the rapid formation of stars and galaxies, while the action background supplied the overarching gravitational framework for the universe to evolve as a whole. We are no longer hunting for a single ghost, but for an entire spectrum of shadows, each revealing a different chapter in the story of the dark cosmos. The search for these cosmic ghosts does more than just map the heavens, it reshapes the world at our feet. The relentless drive to detect the invisible has become a powerful engine for technological innovation, spinning off advances that touch our daily lives in surprising ways. Consider the quest for the perfect detector. To hear the faint whisper of a dark matter particle, scientists needed to build instruments of incredible purity, shielded from the constant background noise of natural radioactivity. This challenge forced the creation of ultra-pure materials and fabrication techniques in pristine, clean room environments far beyond industrial standards. The methods developed are now being used to create superior semiconductors and sensors, pushing the boundaries of computing and medical imaging. The ripple effects continue with the lasers at the heart of gravitational wave observatories like LIGO. To measure a vibration 10,000 times smaller than an atomic nucleus, these lasers must be miracles of stability, their light waves locked in perfect synchrony. The technology developed to achieve this impossible precision is now finding its way into manufacturing, where it guides ultra-fine cutting tools, and into medicine, where it enables new forms of non-invasive surgery with pinpoint accuracy. Even the computational challenge of sifting a cosmic signal from a sea of noise has profound downstream effects. The algorithms created to find one black hole merger in a year's worth of data have become masterclasses in pattern recognition. These sophisticated data processing techniques are the unsung heroes behind modern machine learning, helping to train the artificial intelligence that powers everything from medical diagnostics to financial forecasting. The hunt for the universe's oldest secrets, it turns out, builds the tools for our own future. The weight of a galaxy rests on ghosts. If dark matter is truly a sea of primordial black holes, then the universe is not built on a foundation of exotic particles, but on an archipelago of ancient fossils. Each one is a frozen moment, a perfect snapshot of a specific, chaotic instant from the first second of time. This idea fundamentally reshapes our place in the cosmos. We are not living in a universe filled with an ethereal mist of unknown matter. We are living in a cosmic museum, surrounded by invisible artifacts from creation itself. The largest structures we see, the grand spiral galaxies and glittering clusters, were quite literally built around these gravitational anchors. The connection is profound. It ties the vast galactic scales directly to the microscopic realm of quantum gravity. The tiny, random fluctuations that sparked the birth of these black holes were quantum events, phenomena operating at the smallest possible scale. Those microscopic ripples were then stretched by inflation into cosmic proportions, ultimately becoming the seeds for all the structure we see. The universe we inhabit is therefore a magnified quantum world. The ghost in the machine is not a new form of matter, but the oldest possible form of concentrated gravity. This challenges the very definition of what matter is. We are accustomed to thinking of matter as something made of atoms, something that interacts with light and forces, but these primordial black holes are something else entirely. They are not matter in that familiar sense. They are pure space-time geometry, knots of such intense gravity that they have become independent, permanent features of the cosmos. They are not built from particles, they are built from the fabric of the universe itself, pinched off and set adrift. This means that most of the mass in the universe is not a substance but a shape. It is a landscape of invisible, timeless pits in the fabric of reality. Our solar system, our planet, and our own bodies are just a fleeting afterthought, a delicate shimmer of normal matter moving across this eternal, dark topography. We are the temporary inhabitants of a world whose true mass is made of silent, ancient monuments. What does it mean to exist in such a cosmos? It suggests that the history of the universe is written not only in the light of the stars, but in the persistent, dark presence of its very first moments. We are only just beginning to learn how to read that shadowy text. Despite their elegant appeal, primordial black holes still face a steep climb to become the leading dark matter candidate. The observational evidence has not been kind, placing them in a tight corner. The universe has spoken through three powerful, independent channels, and the message is consistent. Microlensing surveys tell us our galactic halo cannot be packed with black holes between the mass of our Moon and Jupiter. The pristine pattern of the cosmic microwave background rules out a universe where their explosive formation was a dominant, widespread event. And the smooth light from gamma-ray bursts confirms that space is not teeming with asteroid-mass black holes either. These are not minor objections. They are foundational constraints that have systematically closed the door on the simplest versions of this idea. The models where a single, monochromatic population of these objects makes up all of the dark matter. The path forward is no longer about proving they are the sole answer, but about proving they can exist as a significant component at all. This demands a highly specific and finely tuned formation mechanism. Theorists must now engineer a model of the early universe that produces just the right number of black holes across a very narrow range of allowed masses, without creating too many of the forbidden sizes that would have left an observable scar on the cosmos. It is a cosmic tightrope walk. The mechanism must be potent enough to seed the early galaxies and explain the strange LIGO mergers, yet subtle enough to remain virtually invisible to our most sensitive probes. This is the great challenge. We are searching for a ghost that must be massive enough to shape the universe, but rare and stealthy enough to have escaped detection for so long. The mystery of dark matter is therefore far from solved. Primordial black holes represent one of the most compelling and creative chapters in this ongoing investigation, a testament to our willingness to consider the universe's most dramatic possibilities. But the final page has not been written. The true nature of the cosmic ghost remains one of science's greatest enigmas, waiting for the next clue, the next observation that will finally illuminate the dark. This grand cosmic puzzle is not just for professional astronomers in remote observatories. It lives in the questions we all ask when we look up at a starry night. Understanding what holds the galaxies together, whether it is a sea of particles or a swarm of ancient black holes, is part of a much deeper human tradition. It is the same drive that led our ancestors to navigate by the stars and to wonder what lay beyond the horizon. This fundamental curiosity about our place in the cosmos does not necessarily build a faster smartphone or a more efficient car. Its value is measured in a different currency, the enrichment of the human spirit and the expansion of our collective imagination. Every time we invest in answering a question as profound as the nature of dark matter, we are investing in a lifestyle of inquiry. We are choosing to be a species that looks into the darkness and dares to ask, what is there? This pursuit fuels a culture of innovation that radiates outward, touching every aspect of our lives. The children who are inspired by these discoveries today become the problem solvers and engineers of tomorrow. They learn to think in terms of possibilities, to challenge assumptions, and to build the tools that will solve the challenges we cannot yet foresee. The search for invisible black holes is more than astrophysics. It is a declaration that we are not passive inhabitants of the universe, but active participants in its unfolding story. To live with cosmic curiosity is to embrace the most defining part of our humanity, the relentless need to seek answers and to understand the silent architecture of everything around us. Our journey began with a simple, profound mystery, a ghost in the cosmic machine whose gravitational pull shapes the fate of galaxies. We ventured into the heart of this darkness, exploring a possibility as ancient as time itself, that dark matter is not a sea of unknown particles but a vast population of primordial black holes. We witnessed their dramatic birth in the first chaotic second of the universe, forged from the densest wrinkles in newborn space-time. We followed the evidence from the silent echoes of their mergers rippling through LIGO detectors to the powerful constraints drawn from the unblinking light of distant stars and the pristine cosmic microwave background. The case is not simple, nor is it closed. The universe has consistently told us these objects cannot be the only actors on the stage. Yet it has also left the door wide open for them to play a crucial, formative role. They remain a compelling and elegant piece of the puzzle, potentially explaining everything from the impossible maturity of the first galaxies to the strange masses of merging black holes. This story is still being written with every new observation from the James Webb Space Telescope, every tremor detected by LIGO, and every future flash of light catalogued by the Roman Space Telescope. The greatest experiments are still underway, and you have a front-row seat. Stay curious, follow these discoveries as they unfold, and let us know what you think. Do you believe the cosmic ghost is an ancient fossil or something else entirely? Share your thoughts on this grandest of mysteries in the comments below.